You wouldn't allow your young man or young woman to play with this cobra snake, would you? Then why would you allow him or her to continue burning fossil fuels, a more dangerous threat to their safety?
Take young Timmy, for example. He lives in a world dependent on fossil fuels, and if this doesn't change, the consequences could be dire.
The burning of fossil fuels has been inextricably linked to a phenomenon known as global warming, due to the heat-trapping gases released in combustion. Global warming is expected to increase the intensity of forces of nature, such as tornadoes and hurricanes. Other effects of global warming include changes in agricultural yields, melting of glaciers, and the extinction of certain species.
Gee willikers, mister, I don't want to die. What can we possibly do? How can we produce clean energy?
Well, don't worry, Timmy, my boy. We have a vast resource of energy at our disposal, and because of some people's ingenuity, we can now harness a large percentage of this.
Jeepers, mister, what resource are you talking about?
Why, the sun, Timmy. The global energy consumption has been found to be 15 terawatts, and the total energy resource of the sun is 120,000 terawatts. That means we only have to harvest 0.0125% of that to match our energy needs.
Wowzers, mister, that sounds fantastic. I sure do like the sun. But how can we capture all of the sun's energy?
Well, Timmy, there are many ways to capture energy from the sun, but two of the most popular methods are using photovoltaic materials to convert the sun's energy into electricity, or concentrating the energy of the sun and storing it as heat.
Well, gee, mister, that sounds awesome. What's a photovoltaic, though?
It's photovoltaic, Timmy, my boy, and photovoltaics are materials that use energy from photons and light to excite an electron into a higher energy state, and then uses that energy in the form of electricity.
Whoa, whoa, whoa. That's really hard. My brain can't handle that. I think we should talk about the other method of harnessing the sun's energy. Maybe that'll make more sense to me.
Another way to harness the power of the sun involves concentrating its energy to generate heat. These technologies have been placed under the category CSP, or concentrating solar power. Two of the more prominent CSP technologies are solar troughs and power towers. They effectively both perform the same function of concentrating the sun's energy on a specific point to dramatically raise the temperature of the working fluid. This working fluid is then either temporarily stored, depending on the fluid, or sent directly to a heat exchanger where it heats up water to produce steam. From this point on, it is the same process as a fossil fuel powered plant. The only thing that changed is how the steam was produced.
Jeepers, mister, that's incredible! But I'd really like to know more about these power towers and solar troughs.
Well, Timmy, let's start with solar troughs. They're made from parabolic reflectors arranged usually along the north-south axis. This allows the trough to track the sun from east to west. Due to the parabolic shape of the troughs, incoming beams of light are reflected over the line normal to the parabola at the point of contact. This characteristic is useful for concentrating light because all of the reflected rays pass through the focal point of the parabola. A pipe containing heat transfer fluid, for example synthetic oil, is run along the focal point of the parabolic trough, so that incident light is reflected onto the pipe to heat the fluid. Once the fluid is heated by the concentrated light, it is pumped into a heat exchanger to produce steam.
Well, that sounds pretty neat! And swell! How about them power towers?
Well, to me, solar power towers function with the same principle of heating up a working fluid to produce steam. However, instead of having a pipe at the focal point of a parabola, like in the troughs, power towers have a tall receiver in the middle of a field of heliostats. Heliostats are reflectors that track the sun throughout the day, each reflecting the sun's energy onto the receiver, thus heating the working fluid contained inside. Using molten nitrogen salts as the working fluid has become popular because they are relatively inexpensive, have high heat capacity, and have extremely high boiling points. This high boiling point allows the fluid to operate at very high temperatures with no phase change, resulting in a higher thermal efficiency. Additionally, molten salts have the ability to retain the heat for temporary storage in large tanks, which diminishes the effects of solar intermittency. Some advantages of solar tower technology include more efficient production of steam from solar radiation due to two-axis tracking, more efficient generation of electricity from steam due to higher temperature steam production, less parasitic energy usage per plant operation due to reduced movement of thermal mass, a higher capacity factor, meaning more megawatt hours produced per megawatt of installed power equipment, and lower capital costs due to commodity-based inputs, no concrete foundations, and fewer pipes and cable.
Well, that seems really easy to do. Why isn't there more power towers and solar troughs around?
Well, Timmy, it's not as easy as it sounds. You have to consider many things. First, let's look at energy storage. There are two primary methods of thermal energy storage. These include a two-tank direct system and a two-tank indirect system. Let's start with two-tank direct system. A two-tank direct system consists of a cold tank and a hot tank. The cold tank stores the initial molten salts, which are pumped up through the tower that's heated by the concentration of the heliostats. The heated salt is then stored in a hot salt tank. From this tank, the salt is pumped into a heat exchanger, which then produces steam. This steam is then used to power a turbine, which in turn produces electricity. A two-tank indirect system performs the exact same as a direct system, besides the fact that the energy in the molten salt is transferred to a different working fluid, and then that working fluid is used to produce steam. Both of these storage systems heat salts to temperatures up to 500 degrees. Due to this high temperature, the plant can run for up to 15 hours without solar radiation.
But how do you turn all that energy into electricity? And what's a heat exchanger?
Well, Timmy, my boy, you can use the energy for more than just the creation of electricity. You can use the heat to force other reactions like the reformation of ethanol. However, using the heat to generate electricity is one of the most prominent applications, and this is done, as was previously mentioned, with a heat exchanger. The most commonly used heat exchanger, and the one most frequently coupled to CSP, is the boiler. To reiterate, the principle behind a boiler is quite simple. Thermal energy is transferred to water to produce steam. Let's take a closer look at the heat exchanger, Timmy. As you can see, this heat exchanger consists of two main parts: the shell side, which contains the water to be boiled, and the tube side, which contains hot working fluid. This fluid is then passed into the exchanger through many small tubes, which serve to increase the surface area between the working fluid and water, which increases the rate of heat exchange. The tubes wrap around in a U to save space. As you can see, in the center of the exchanger are baffles. These baffles serve to direct the water as it travels through the exchanger, mixing it and preventing the water from traveling directly from the intake to the output, prolonging the amount of time in the exchanger. If you're still confused by what exactly happens inside a heat exchanger, this diagram shows a three-dimensional view of water as it travels through. The red and orange lines, which show the water at its hottest point, are swirling around the inside of the exchanger directed by baffles inside. This hot fluid enters through the top and leaves through the bottom, at temperatures much cooler than the inside of the exchanger. Let's look at some of the math. According to Newton's laws of cooling, the rate of change in energy of a small volume of fluid is proportional to the difference in temperatures between it and the corresponding element in the other pipe, here represented by T1 and T2. The rate is also proportional to the surface area between the two temperatures and the thermal conductivity constant K, We can use this really simple example to model the more complex problem of two fluids flowing through the pipes. If we assume that their temperature profiles are independent of time, then after a little mathematical manipulation of Newton's law of cooling, we can get to a pair of coupled ODEs, which accurately plot the temperature distribution across the pipe length. This diagram shows the differences between heat distributions when the fluid is flowing concurrently, as shown in the diagram above, and countercurrently, as is shown in the diagram below. As you can probably guess, Timmy, the countercurrent flow is ideal for transferring as much heat as possible to the surrounding. Take a look at this graph. It plots the ODs we talked about before over pipe distance. You can see that the further the fluid flows, the more heat that is exchanged. Eventually, the two fluids reach an equilibrium stage in which no net heat is transferred.
Well, all this stuff seems pretty cool, but are people really gonna buy into it?
To answer that question, Timmy, let's consider a techno-economic analysis. Let's do an analysis of a solar power tower plant. When looking at a solar power tower plant, one will notice that the average cost is around $650 million. 30% of this cost goes to the cost of heliostats, which includes installation and maintenance. When looking at a breakdown of the total cost of the power plant, one may notice that the heliostat, in red, takes up a large portion of the cost. The next largest portion of the graph is the gold portion, or the indirect cost. This includes government taxes on the land and building of the power plant. By far the greatest cost, the heliostats are the one portion of a concentrating solar power plant that can be improved upon to drastically reduce the price of this energy. Take my friend Tom. Tom started a company that plans on cutting the price of heliostats in half, making them $100 per meter squared. This would allow concentrating solar power plants to come online and be competitive with coal power plants.
This magic number of $100 per meter squared, I think, is attainable for heliostats.
And because of companies like Tom's that are committed to making solar energy more affordable, you're sure to see more concentrating solar power plants in the future.
Well, that sounds super swell, mister. Now I know how to energize my future.